Okay. In the note, it is stated that while considering the Poisson brackets, we discussed about two functions of 2n variables, but when we discussed about the Lagrangian brackets, we were having 2n functions and 2 variables. Now we are having the canonical character of a transformation in terms of Lagrange brackets. To obtain the canonical character or the conditions, first we will show that if we are having a transformation qi tilde, pi tilde, which are the functions of t, qi and pi, then the canonical transformation can be considered as independent of t. Means if we are having a transformation that depends on t and then replacing t with some particular values, the transformation so obtained will also be canonical. And hence replacing t with a particular value of t at some particular instance of time, we are still having the canonical transformation. And then reversely we will assume that the transformation is canonical for every possible value of t. Then we will show that for arbitrary t it is a transformation, means it can be assumed to be dependent on t. So with these two things, we can assume that if the canonical transformation depends on t, then we can assume that that very transformation does not depend on t, means it is independent of t. And after that, when we will obtain the canonical character, we will find out that character by considering those mappings which are independent of t. Okay, so let's start it. Here we are just assuming that the transformation qi tilde is phi I t qk pk and pi tilde is psi I t qk pk for ik from 1 to n, and it is canonical. Now all of you know that the necessary and sufficient condition for a transformation 1 to be canonical is that there is a generating function f that will be a function of t, qi and pi, and the constant c that is termed as the valence, such that the condition 2 holds, that summation I from 1 to n pi tilde delta qi tilde minus h tilde delta t should be equal to c into summation I from 1 to n pi del qi minus h delta t minus delta f t qi pi. Now we are assuming that the canonical transformation, the transformation 1 is canonical. So the identity 2 holds, and if we replace t with a particular fixed value t bar, then the variation of t will be 0, and so equation 2 reduces to 3, means it will be summation I from 1 to n pi del qi tildes is equal to summation I from 1 to n pi del qi, there is c also, minus delta f, t is replaced with t bar qi pi. Okay, and now equation 3, which is the defining identity for a transformation, is independent of t. Okay, so we are considering 4. It's just derived from equation number 1 by replacing t with a particular value t bar. So that formulas for the transformation in 4 is canonical with valency if it satisfies 3. And so we can say that if for arbitrary t the transformation is canonical, then it is canonical for a particular value of t bar also. On the contrary, if the transformation obtained from 1 by replacing the variable t with a various fixed value t bar are canonical with one and same value, means for every possible value of t, we are having the same valency and the same function h tilde, then defines h tilde to be equal to ch plus curly f by curly t plus summation I from 1 to n pi tilde del qi curly qi tilde by curly t. And now replace this value in equation number 3, means using 4, 5, 3 into, we will obtain that equation number 1 is canonical. Okay, so what we proved, that if the transformation depending on time is canonical, then it is canonical for every possible value of t bar for a particular value. And if the transformation for every possible particular value of t is canonical, then it is canonical for arbitrary value of t. It means if the canonical transformation is dependent on time, we can assume it to be independent of time. And if it is independent of time, we can assume it to be dependent on time. Okay. Now, let's try to find out the canonical character. For that, we are just taking those canonical transformations which are independent of t. So qi tilde is phi I, qk pk, pi tilde psi I, qk pk, and then its Jacobian is non-zero. With this condition, which is the condition, necessary and sufficient condition for a transformation to be canonical, here del qk tilde will be equal to the variation of qk tilde. It will be summation I from 1 to n variation of qk with respect to qi del qi plus variation of qk tilde with respect to pi to del pi. Now let's define capital phi I and small capital psi I, two functions. Capital phi I is summation k from 1 to n pk curly qk by curly qi minus cpi, and psi I is summation k from 1 to n pk tilde curly qk tilde by curly qi. Now replacing the values of 10, 9 in 8, we will obtain summation k from 1 to n capital phi I del qi plus capital psi I del pi is equal to minus del k qk pk. Now, all of we know that the equation number 11 and the term on left hand side is differentiable if the following relations hold, that partial derivative of phi I with respect to qk should be equal to partial derivative of phi k with respect to qi, partial derivative of psi I with respect to pk should be equal to partial derivative of psi k with respect to pi, and partial derivative of phi I with respect to qk should be equal to partial derivative of psi k with respect to pi. So now replacing these values from 12, 13 and 14 in 10, what we will obtain? Oh, sorry. The relations 16, 15, 16 and 17. Okay, and if these relations are obtained, now the equation number 15 is the Poisson bracket of qi qk. Equation number 16 is Poisson bracket of pi pk, and equation number 17 is Poisson bracket of qi pk. So we are having these relations. Poisson bracket of qi qk is 0, Poisson bracket of pi pk is 0, and Poisson bracket of qi pk is c into delta ik. So this is the canonical character, or we can say this is the necessary and sufficient condition in terms of Lagrange brackets for a transformation to be canonical. Okay. After that, we are defining the Jacobian matrix of a canonical transformation. Consider M to be the Jacobian of qi tilde, q1 tilde, q2 tilde, qn tilde, p1 tilde, p2 tilde, pn tilde with respect to q1, q2, qn, p1, p2, pn. And J is a 2n by 2n matrix like 0, minus identity, identity and 0. Here identity is the matrix of order n by n, and this 0 is the 0 matrix of order n by n. Okay, so from here it's an exercise for you people to obtain that M transpose Jm will be equal to Cj. And for a univalent canonical transformation, C is 1. So M transpose Jm will be equal to J. After that, we are having the conditions of canonical transformation of a transformation in terms of Poisson brackets. The similar article is obtained for Poisson brackets also using the Jacobian matrix and its relations. These are just the simply relations, and then all the procedure is similar. So the same conditions are obtained. Okay, after that, invariance of the Poisson bracket in a canonical transformation. This is also simply based on the transformation, and it is proved that it remains invariant. Okay, like as we have discussed recently that when t is replaced by fixed values, it is invariant. The same things are here. So you can read it. If found any problem, I don't think it will happen, but if found any problem, we will discuss in the next lecture. Okay, so at this point,